All right, welcome back to class. The plan for today is we're actually going to continue with 11.2 on series. Um, and then we might, post a bit of the 11.2 material if we don't quite get everything done, if we don't quite get to all of the applications. Might post that as a supplemental lecture, or I might end up posting all of 11.3 as a supplemental lecture. I'm going to kind of look at where we are in the schedule after today's class and make that call. But we are going to spend an extra lecture on 11.2 on series because I really do think that this is important foundational material that that we want to make sure that we get down well. Also, I need to cancel class on Monday, April 7th, so a couple weeks out still, but just wanted to give you a heads up on that. I have a committee meeting that I kind of have to be at that unfortunately we have like 10 or 12 or something people on the committee, and there's really no good time that works for everybody. So it ended up being the meeting ended up being right during our class time, so I have to cancel class that day. But I will post a makeup lecture to YouTube to make up for that missed class, and more information on that, whenever that when we're a little closer to that date. The quote of the day. The outcome of any serious research can only be to make two questions grow where one grew before. And I think this gets at the point that if you're doing any real research, I mean not just trying to answer some little tiny question, but if you're doing any research into any kind of real interesting problem, um, typically when you answer one question, you find, two or three or four more questions that naturally come out of the pursuit uh, of answering that one question. So I think the kind of serious researcher, the person who's, and this doesn't necessarily have to be in science or have to be in formal research. It can be in, you're just curious about this field and you decide to, watch some YouTube lectures on it or read a couple books on it or something. If you take that seriously, you'll find that you end up with more questions than you started with. Now you've answered a bunch of questions along the way, but you end up with more questions. And I think the folks who have a tendency to, you know, to investigate something and answer questions and then end up with no questions at the end, they're the ones who were, I think, kind of looking for a certain answer in the first place, and they got their answer, and they kind of, even if they kept reading the book or, whatever it is, following the course of the research, maybe the wheels stopped turning as soon as they, kind of confirmed what they thought was true, and they said, "Oh yeah, look, I was right all along," right? So I think this ties closely in with that conceit of knowledge question, right? If you're really approaching research the right way, I think it really does keep you humble. You kind of realize how little you know and how much more there is still to explore. And the more that you explore, the more that you see how much more there is still to explore. And kind of in that vein, one last plug for the Philosophy of Science course this coming fall. I don't think registration's open yet. I think it's maybe about a week or so. But the Philosophy of Science course is up in the catalog. This is a course being offered by our philosophy professor, Drew Van Land. Uh, he is offering this for the first time this fall, and it sounds like a really interesting course. I wish I could take it, but it doesn't really work with my schedule these times. But it is three credits, no prereqs, so you don't need any previous philosophy or anything like that coursework. It's Monday, Wednesday, 12 to 1:15 on Allegheny campus. Um, I think remote modality works great for a lot of courses, but I can see the idea with a philosophy course where you want to have kind of active discussion and debate, having that in person. For whatever reason, people tend to just interact with one another very differently in online or even remote settings. Even if we're all on Zoom and looking at each other and it's more of an interactive session, people do still tend to act a little differently than if they were face to face. So I have a feeling that's why it's on campus. And here's the blurb um, from the catalog, but I think this sentence kind of lays out the idea of the course that students will practice using the abstract insights of philosophy to both learn scientific subject matter more effectively and to critically analyze scientific claims. So, being in Calc 2, a lot of you are planning to go into scientific type fields. But even if you're not planning to be a scientist even if you're not planning to go into a scientific field and you just, enjoy calculus and that's why you're taking the course, um, we're constantly being bombarded with claims these days. And we often ask questions like, okay, or maybe we should be asking questions like, okay, this person made this claim. Uh, on what basis can they make that claim? How can they substantiate that claim? And we're typically not looking for an answer like, at least hopefully not like, well, I have this degree, so you should just believe me. Or, we're typically not asking for things like mathematical proof. Most of the claims that are made don't really lend themselves to that kind of argument. So how do we analyze scientific claims? What does it even mean for a claim to be scientific versus a claim of a different nature, right? I mean, probably things like, the existence of God or something, I think we would probably say is not really a scientific debate. It's a different kind of debate. Um, so yeah, I mean, I think this would be a really interesting course for anybody going into the sciences, certainly, but even anybody that just wants to think a little bit more about this. What does it mean when somebody makes a claim to ask what evidence do they have that substantiates that claim? Okay, so and if you have more questions, reach out to Professor Van Land. This is about all that I know about it between this and my few-minute chat with him a couple weeks ago. So. Um, All right, so moving back into 11.2 series. Just a really quick recap, because as I mentioned several times last time, sticking to the definitions, understanding the premises is so important in these kinds of tricky um, situations that have infinities floating all around everywhere. So a series, roughly speaking, is the sum of the elements of a sequence. It's an infinitely long sum. And the way we evaluate convergence of a series is using partial sums. So we look at the first n elements of the series, and we call that the nth partial sum. We say that a series converges if the sequence of partial sums, the first partial sum being just a1, the second partial sum being a1 plus a2, that's the second partial sum, the third partial sum a1 plus a2 plus a3, that's the third partial sum, that forms a sequence. If that sequence of partial sums is convergent to a real number, to a limit in R, then we say that the series is convergent and we say that its sum is that real number. We have to be very, very careful whether we're talking about sequences or series, whether we're talking about the individual terms of a series, or whether we're talking about the series overall, or whether we're talking about the partial sums, which are sums of individual terms. There are a lot of really closely related concepts that are different. They're related to one another. They look very similar. Sometimes at the surface level, it's easy to confuse them, but they're very different ideas. We have the test for divergence, or the divergence criterion, that if the individual terms, now we're looking at the individual terms of the series, if the individual terms do not go to zero, then the series must diverge. However, it needs to be pointed out that the individual terms going to zero, it's a necessary condition for convergence, but it's not a sufficient condition. If the individual terms go to zero, the series might converge, but it might not. And we will actually see a counterexample today where we have a series with terms that go to zero, but the series diverges. And a corollary, the contrapositive is true, that if a series converges, then its terms go to zero. So the test for divergence looks at the terms individually. Our definition for convergence of a series looks at the sequence of partial sums. It looks at the partial sums kind of individually. Okay. We also talked quite a bit about the geometric series. Consider the series sum I equals 0 to infinity of r to the I. So that's 1 plus r squared plus r cubed and so on. And we said that this series converges if and only if absolute r is less than 1, if r is strictly between -1 and 1. And in that case, it converges to 1 over 1 minus r. It diverges otherwise. I mentioned a warning with kind of an example here that even something as simple as applying an associative property, which we think of as uh, almost so basic of a property that we don't even think about applying it often, but we don't even, think, oh, I'm using the associative property here. We just kind of do it. Um, but even something as simple as using an associative property in the infinite series can lead us astray. We have to be very careful when working inside of an infinite series. However, when we pass to the partial sum, kind of any of our standard algebra goes, right? Once we're in our partial sum, we don't have infinitely many things added together. We just have a bunch of things. It might even be like 100 million things, but it's still just a finite number of things. And all of our good old commutative, associative properties, all that kind of stuff, uh, distributing, factoring, et cetera, works just fine within the partial sum. Okay, so with that really quick recap, um, let's move on to the next example here. So I want to compute this sum. So I want to compute sum I equals 1 to infinity of 2 over 4i squared minus 1. Now, one thing I might look at if I'm investigating this is the 2 over 4i squared minus 1. I could use partial fractions, and I see that I can write this as 2i minus 1 and 2i plus 1. The bottom will factor into that, and I can write this as some number over 2i minus 1 plus some number over 2i plus 1. And I think it turns out that if we have ones in the numerator and we put a minus uh, here, then I get, when I bring everything under a common denominator to get under one fraction, I have 2i plus 1 minus 2i minus 1. So my 2i's go away and I have plus 1 minus and minus 1 is 1 plus 1 is 2. So when I'm within an individual term, I can see that this is 1 over 2i minus 1 minus 1 over 2i plus 1. Or I can see that this series is going to be, well, when I equals 1, I have 1 over 2 minus 1, that's 1 over 1 minus 1 over 2 times 1 plus 1 is 1 over 3. That's the first term of the series. Then the next term, when I equals 2, 1 over 4 minus 1 is 1 over 3 minus 1 over 2 times 2 plus 1, 1 over 5. So this is my I equals 1 term. I equals 2. I equals 3 term is going to be 1/5 minus 1/7, and so on. There was a good reason I gave this warning up here is that I'm very tempted to just regroup these this way and say this equals 1. But I see that I have to be very careful when doing that, right? If I just use my associative property and regroup the minus 1/3 plus 1/3, the minus 1/5 plus 1/5, the minus 1/7 with the next plus 1/7, and so on, I don't have a rule that says I can do that. And in fact, in general, I see that I can't do that. That would, at least in one case, just moving the parentheses like that leads to a contradiction. But I still want to do something like that. But what I can do is I can look at the nth partial sum. So this is I equals 1, I equals 2, I equals 3. Let's try I equals n minus 1, and then I equals n. So for I equals n, I'll do that one first. That's 1 over 2n minus 1 minus 1 over 2n plus 1. When I is n minus 1, So the second term from the end of this nth partial sum. So let me do this over here in my scratchwork area as well. So 2 times n minus 1 is 2n minus 2 minus 1 is 2n minus 3 minus, and then of course 1 over 2n minus 1. Going from 2i minus 1 to 2i plus 1 just adds 2. Now, I couldn't shift my parentheses. I couldn't regroup things in my infinite series. But in my nth partial sum, this is just a bunch of stuff, maybe 100 things, 1,000 things added together, but it's a finite number of terms. I can do all of my commutative, associative properties, distributive properties, any of that in my partial sum. So now it's fair game to move my parentheses around. I'm going to cheat here a little bit and just kind of erase everything, erase all my parentheses. And I see that the minus 1/3 plus 1/3, they go away. I'm in my partial sum. I can do this. Minus 1/5 plus 1/5, they go away. Minus 1/7 is going to have a plus 1/7 over here. My 1 over 2n minus 3 added on is going to have a minus 1 over 2n minus 3 that cancels it out. Minus 1 over 2n minus 1 plus 1 over 2n minus 1. And all importantly, I'm left with this vestigial minus 1 over 2n plus 1 that doesn't have anybody to cancel it out. I wouldn't have seen that if I tried this in my series, right? All of my partial sums have a little bit at the end that doesn't go away. Is that a problem here? So I see that Sn equals 1 minus 1 over 2n plus 1. Or my sequence of partial sums this is my sequence of partial sums, and I do see that this converges. As n goes to infinity, this converges. Well, this 1 over 2n plus 1 goes to 0. This does converge to 1. So in this case, if I applied my moving the parentheses, my associative property, to the series, I would have happened to get the right answer, but I can't count on that being true all the time. What was really necessary was that this bit here went to 0. This vestigial stuff goes to 0 in this case, which is kind of the magic that makes this work out nicely. In this case up here, I always had a 1, and then I always had a minus 1 left over at the end of the partial sum. And this does not go to 0. It stays minus 1 forever. So, right, that was the hang up here. So I pass to the partial sum. I do my cancellation in the partial sum. Everything actually turns out pretty nicely. And then I can see that my sequence of partial sums does converge to 1. Therefore, I can say that my series converges, and it converges to a sum of 1. There's a specific name for this kind of a series where once we pass to the partial sums and use our associative property, we get massive cancellation, and we just end up with essentially a first term and a last term, or maybe like a first 2 terms and a last 2 terms or something like that. We call this a telescoping sum. You ever seen those, like, old time pirate telescopes? I don't know if they even actually are real, like, but where it's like really small when they like go like this and it telescopes out and you push it together, they all kind of like nest inside of one another. So this telescoping sum, it starts out as really long and it kind of collapses to only a couple of terms. We get a lot of cancellation of the interior terms, and it's just the exterior, the first and the last term, or maybe the first 2, last 2 that show up. We call that a telescoping sum. The nice thing about a telescoping sum is that I can write a closed form expression for the nth partial sum, and then I can evaluate that with limits pretty easily. It's hard to evaluate a sum with limits whenever there's a whole bunch of terms, and as n gets bigger, we get more terms. We can maybe say what's going on with each term individually, but getting more terms makes it more confusing. Okay, so that's an example of a telescoping sum. So let's look at another example. Let's try to write a repeating decimal as a ratio. We have this like, I think like everybody from, I don't know, seventh grade or something on has this idea that like rational numbers that can be written as fractions, their decimal expansion either terminates or repeats, right? So like 1/3 famously is 0.333 repeating. So not all fractions have a decimal expansion that terminates. Not like 1/4 is 0.25 and that's the end of it. But all fractions, rational numbers, integer over integer, their decimal expansion terminates or repeats. Well, if it terminates, we just move the decimal point to the end and divide by a power of 10, and there's your rational number. Divide out common factors if needed. But if it repeats, it's not so easy. Let me try to write 0.08 repeating as a ratio. How can I do this? How can I work backwards and say, what's the fractional form of 0.08 repeating? And you might know just by like recognition or something how these work, but let's actually try to show it carefully. You might be able to kind of guess what this is, but let's go through it carefully. Well, what's 0.08 repeating? It's like trying to write this quickly and not sloppily, and it's like that, right? Or really, I can group these as like this thing, and then the repeat, and then the repeat, and then the repeat. Or this is actually like, from this first one, it's like 8 times 10 to the minus 2. From the second one, 8 times 10 to the minus 4. From the third, 8 times 10 to the minus 6, and so on. I really see that 0.08 repeating is an infinite series. So it's something like sum I equals 0 to infinity. I'm starting as 0 for a specific reason here. 8 times, and then I have 10 to the power. I want -2, -4, -6, so that's going to be -2. And then when I is 0, I want this to multiply 1. When I is 1, I want it to multiply 2. When I is 2, I want it to multiply. Sorry, I think I said that wrong. When I is 0, I want my -2 to multiply 1. Oh yeah, no, I said it right. Yeah. 0 goes to 0 goes to 1, 1 goes to 2, 2 goes to 3. So I need I plus 1. So the exponent up here, -2, is -2 times 1. -4 is -2 times 2. -6, -2 times 3. So I want to multiply my -2 by 1, 2, 3 when I is 0, 1, 2. So I see that's got to be I plus 1. I'm going to be a little bit sloppy here with my my details. I'm going to actually factor an 8 out of here. We could pass into the partial sum, factor the 8 out, and make the argument there, but I think we can kind of see that this is basically a geometric series, and I think we could imagine that if a series converges, then a lot of stuff is going to work. A lot of our more fundamental algebraic properties are going to work a lot nicer. So particularly things like factoring a number out like this is not a problem if the series converges and has nice convergence properties. this really feels like a geometric series. So really, what is this? 10 to the minus 2 times I plus 1. Let me try to make it look more like a geometric series. Well, it's 10 to the negative 2I times 10 to the negative 2. I think this 10 to the negative 2 can come out. That's going to be 8 over 10 squared, or let's say 8 over 100, times sum I equals 0 to infinity of 10 to the negative 2I. Well, this is 1 over 100 to the I power. So I pulled off this factor of 10 to the negative 2 and brought it outside. Then the 10 to the power negative 2I is 10 to the negative 2 to the I power, or 1 over 100 to the I power. But this is exactly a geometric series with a ratio of 1 over 100, which is indeed a negative 1 to 1. This is a convergent geometric series. This is 8 over 100 times 1 over 1 minus 1 over 100, 1 over 1 minus r. Or this is 8 over 100. Well, I suppose I can just multiply that 100 through in the denominator. So it's really just 8 times 1 over 100 minus 1. Or it is 8 over 99. And we could actually make an argument like this pretty generally, that so if I have a number that repeats every 2 decimal places, whether it's 0.08 repeating or 0.13 repeating or 0.74 repeating, if it repeats every 2 decimal places like this, I can take the number, in this case, the number 8, for instance, or the number like 73, divide it by 10 squared minus 1, the number 10 to the number of decimal places, subtract 1, and that's my ratio, that's my fraction. Or if it repeated every 3 decimal places, I take the number and divide it by 999, 10 cubed minus 1. We can see that pattern is going to come out of the geometric series. For time considerations, I was a little hand-wavy about my ability to factor stuff out here, but geometric series, when they converge very nicely, and we don't have to worry about that kind of stuff. So that's kind of a side note. But so one example of geometric series that maybe substantiates, a claim that you've heard for a long time and even gives a little more solidity to, maybe you knew this pattern just kind of by observation that you're dividing by 9 or 99 or 999, something like that. But maybe this gives a little more substance to that claim. Okay, so getting to a really important series, the harmonic series. The harmonic series is the sum of 1 over the positive integers. So 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4, etc. Clearly, the individual terms go to 0. So we wouldn't say, we would not make the claim this series diverges by the test for divergence. However, we would also not make the claim that because the test for divergence doesn't say the series diverges, then it must converge. That's not a valid claim to make. That's not a valid conclusion from the test for divergence. The individual terms go to 0, it might or might not converge. And our claim is actually that this series diverges even though its terms go to 0. The criterion for convergence is something like the terms have to go to 0 fast enough. They have to get small enough fast enough to converge. Just getting small isn't enough to converge. You have to get small enough fast enough. Let's investigate this. Let's give some substance to this claim. So let me think of this series. 1 plus 1/2 plus 1/3 plus 1/4, and so on. I can think of each of these terms maybe as areas. I have an area of size 1, an area of size 1/2, an area of size 1/3. And maybe it's an area of a rectangle with, say, height 1 and width 1, height 1/2 and width 1, height 1/3 and width 1, and so on. So I have height times width, height times width, and so on for each of these rectangles. And I can put these rectangles on an axis, or on a two-dimensional set of axes here. And I'm going to put my rectangle of height 1, it's going to have width 1. I'm going to put that rectangle of height 1. Maybe I'll try to do this a little bit color-coded to keep straight what's what. I'm going to put that here in between 1 and 2. So it has width 1, and my scales are not the same between the horizontal and vertical, but has height 1. So that's this, we'll call it A area. And then let's use blue for this one. Between 2 and 3, I'm going to put my rectangle again of width 1, height 1/2. I'll call this maybe B. And then height 1/3 between 3 and 4, C, rectangle C. Height 1/4 between 4 and 5, that'll be like D, and so on. So the question is, can I add up all these areas? Well, one thing I notice about these areas is their upper leftmost point is like 1, 1, 2, 1/2, 3, 1/3, 4, 1/4, and so on. I can imagine a curve going through each of these points. And I can imagine the curve f of x equals 1 over x. Why did my x come out so wonky there? 1 over x on 1 to infinity, maybe being this curve. So I have, let me do something a little inappropriate here, but I'll just call this sum S. I really don't want to say that it's equal to S unless I prove that it converged and it converges to S, a real number, but let's consider this area S. And I kind of roughly speaking see that the area S, these boxes, these rectangles are made by piecewise constant functions. A piecewise constant function isn't decreasing on the interval over which it's constant, and f of x is decreasing on the positive real line. So I see that if this sum exists, it's got to be bigger than integral 1 to infinity 1 over x dx. This is the idea that I want to use. Now, okay, we want to be a little more careful than this. Like, we see that this is a good idea, but we need to really tighten up the details here. So let me actually take a step back and say, all right, how can I take an idea like this and make it more formal and make it appropriate so that we are actually using our definitions very carefully? Well, our definition actually requires us really to think about the sequence of partial sums. So maybe I should reimagine this idea in terms of partial sums. So let's look, for instance, at uh, maybe S3, 1 plus 1/2 plus 1/3. Let's look at this partial sum. I can do exactly the same thing. I'll do it quicker. I won't take as much time harping on all the details. Let me keep my color scheme the same so we can see what's what here. Okay, so what I see is that S3, 1 plus 1/2 plus 1/3, imagining it as these areas of these boxes, must be bigger than the integral. I got to be careful here. It's easy to be kind of off by one if any of you have ever done any programming. And off by one error is like very common, right? Miscounting by one. I need to integrate from 1, where my left end of my first box goes or starts, up to 4, not up to 3. That would only like include the first two boxes, but it's got to go to 4. So integral from 1 to 4 of 1 over x dx. Or 4, well, that's just n plus 1 for the nth partial sum, right? So I see that my nth partial sum, Sn, has to be bigger than what? Integral 1 to n plus 1, 1 over x dx. Or that's what? Log n plus 1 minus log of 1, but that's 0. So Sn has to be bigger than log n plus 1. But this means that limit n goes to infinity, Sn has to be bigger than or equal to limit n goes to infinity of log n plus 1. But wait, log n plus 1 as n goes to infinity, that is an infinite limit. And limit Sn has to be at least that big. Sn goes to infinity, the series, sum 1 over n equals 1 to infinity, diverges. It diverges quite slowly, but if you plug it into your calculator and you pick a certain decimal place to look at, if you go far enough, that decimal place is going to keep ticking over, right? If it was going to converge, if you pick a certain decimal place to look at, you go far enough, that decimal place stops moving, and only the ones to the right of it keep moving. So this diverges. It diverges very slowly. It diverges like, logarithmically, which is quite slowly, but it does diverge. And we can even actually say a little bit more here. We can look at another function that's shifted over 1 unit. What would this function be? It would be 1 over, well, what would it be? X minus 1. So I wanted to go through 2 comma 1 over 1. I wanted to go through 3 comma 1 over 2 and 4 comma 1 over 3. So if I imagine the function that is 1 from 1 to 2, and then 1 over x minus 1 from 2 on, so I have a lower bound for Sn. Let me generate an upper bound. Sn is, or well, let's start with S3. S3 is less than what? Less than 1 plus, so 1 is this area here, plus the integral from 2 to 4 of 1 over x minus 1 dx. Or really, I see that that S3 related to 4 is the same n to n plus 1 relationship that I saw before. So this is really Sn and n plus 1. But that's 1 plus, well, this is log x minus 1 evaluated at n plus 1. That's log of n plus 1 minus 1. That's log of n. Minus log of 2 minus 1. That's log of 1, which is 0. So an upper bound for Sn is log n plus 1. So interestingly, we have bounds on Sn. Sn has to be bigger than or equal to log of n plus 1 and less than or equal to log n plus 1. So if we get to our block stacking problem, which we definitely won't get to in this class, this inequality is very helpful there. We actually have a bound on Sn above and below. Log n plus 1 for large n is pretty darn close to log n. So these bounds are about 1 unit apart. We can know Sn to say within about half of a unit of its actual value, more or less, for large n's, just by plugging in here. We don't have a nice explicit formula for Sn. We got kind of the next best thing, a pretty tight upper and lower bound on Sn as explicit formulas. So that's kind of just a nice, we've proven it diverges using only the green one up here, but we took that a little bit further and got an upper bound on Sn as well for use later on. But the harmonic series is a very nice counterexample to remember. Right? It's a counterexample for a lot of things you say, hey, there's this theorem that says this. I wonder if it says something similar. First thing to ask yourself, does it give the right answer for the harmonic series? And often the answer, often if the thing that you're thinking of doesn't work, it won't work for the harmonic series. So harmonic series is a good series to have in your back pocket for counterexamples. If you think that something might be true, see if it gives the right answer for the harmonic series. For instance, if you think that it might be true that if the individual terms go to 0, then the series converges, well, these terms go to 0, series does not converge. So that can't be the case. We found a counterexample right here that disproves the opposite of the criterion for divergence. Okay, let's look at a couple applications of the geometric series. So the first application we're going to look at, we might only get through this one, and then I'll kick the other applications to a supplement. The first application is the bouncing ball. So if we imagine, we're thinking in one spatial dimension here, so we pick a ball up, we're holding it there, we let it go, and it bounces straight up and down, and we visualize its height as a function of time. So the horizontal axis is time. The vertical axis is the one-dimensional height. And let's say we drop it from a height h, height capital H. I'm going to cheat a little bit here because I don't want everything to be off by like half of a unit. So really we're going to pretend that we like shoot it up from the ground with enough energy to get it up to height capital H, and then it falls and just kind of bounces from that point forward. Mainly because I don't want to deal with a whole bunch of indices being off by like 1 unit or something. So our ball is going to bounce up or come up and then back down, and it's going to impact. So it maybe comes up to a height of, I don't know, say 5 feet. Now, in the real world, of course, we never have perfectly elastic collisions. When it impacts the ground again, it hits the ground, it kind of, roughly speaking, pushes some energy into the ground, and the ground pushes energy back into it and kind of throws it back up again. But there's going to be some energy lost in the form of heat or of you know, putting some of that energy into the ground and maybe moving the ground a tiny bit, or in noise vibrations, something like that. Some of that energy is lost. So when it bounces back up, it doesn't go quite to the same height. It's it bounces a little bit shorter. Well, the height of this peak, if this peak is at height h, this peak is at height h times something. This thing is related to the COR, the coefficient of restitution. So the COR is the coefficient of restitution. It's kind of like something like the percent of energy that gets returned to the ball. The ball had a certain amount of potential energy here when it was at rest. It has a certain amount of potential energy here. That energy has gone down by a factor of the COR squared. How much of that energy is given back to the ball versus lost? Um, there was something that I wanted to say about that, but and different materials and different objects have different CORs. So something like a lacrosse ball or something that's quite bouncy, or like one of those little, rubber bouncy balls that seem to just bounce forever, they'd have a very high COR, close to 1, maybe 0.95 or 0.9, where something like, a bean bag that you throw in a cornhole or something has a COR very close to 0. And you can imagine things in between, right? Things that bounce a little bit, but don't bounce all that much. But then it's going to do the same thing, right? It's going to come down, hit again. It's going to get some of that energy returned to it, and it's going to lose some of the energy. But it fell from a height of h times COR squared. It's going to get yet another COR squared factor, meaning it's going to come back up to height h times COR to the 4th. And then it's going to do it again, h times COR to the 6th, and so on. Keep in mind, this is in one dimension, so the ball is only bouncing straight up and down. The left to right, uh, deviation here is just measuring time. So we're going straight up and down. So to go from here to here, the ball has traveled a distance 2h. It's gone up h and then straight down h. From here to here, the ball has gone up h_COR squared and down h_COR squared. Right. So an interesting question is, what's the total distance the ball travels? We see it's going to keep, in theory, bouncing forever. And by the way, COR is between 0 and 1. It can't be 1 in the real world because we're always going to lose some amount of energy into the environment. So it's between 0 and 1. What's the total distance the ball travels? It's going to keep it has infinitely many bounces. Well, it's going to be the sum. I equals what? Well, let me write it out first. So the distance is going to be, well, it goes up h and then down h, so that's 2h. And then it goes up h_COR squared, down h_COR squared. And then it does that for CR to the 4th, and so on. If I factor out a 2h here, again, I'm being a little sloppy here. this is going to be a convergent geometric series. It converges very nicely. But if I factor out a 2h, I can get 1 plus, and I see everywhere that as COR pops up, it's kind of to an even power. So I'm going to just think of COR. But in fact, let me just come over here and say x equals COR squared. So this is going to be 1 plus x plus x squared, x to the fourth, and so on. Or this is really just 2h times the geometric series, sum I equals 0 to infinity, x to the I, where x is COR squared, but COR is strictly between 0 and 1, so COR squared is strictly between 0 and 1. If I square a number that's between 0 and 1, it stays between 0 and 1. But that means this is a geometric series that converges, and it converges to 1 over 1 minus x. Or it's 2h over 1 minus COR squared. So if my COR was 90%, COR squared would be 81%, 0.81. 1 minus 0.81 would be 0.19. I take 2h over 0.19, or that's roughly 2h times 5. It would bounce about 10h. That will be the total distance it covers. It covers a finite distance over an infinite number of bounces. We can also ask about the limiting case. What happens if COR gets closer and closer to 1, or what if COR were to equal 1? Well, then we just have 2h plus 2h plus 2h forever. We have something that goes to infinity, and that makes sense. If the ball just keeps bouncing infinitely many bounces and the bounces never get shorter, then it bounces an infinite distance. So that's our distance. The total distance traveled 2h over 1 minus COR squared. If we were to do kind of the original setup and we were to drop it from height h, then we would have to subtract 1h off of the front. So if we were just dropping it from height h, then we just have to subtract h, which, not a big deal, but it would be annoying to keep track of that all along here. So that's why I just pretended that we just shot it up from the ground at a velocity that made it go up to height h and then keeps going. But if you wanted to drop it from height h, just subtract h off of here, subtract this leg off, and then there you go. All right, any questions on this application? I don't think in 6 minutes we have enough time to talk about a reserve rate, but this is a finance and economics example where we'll see the geometric series pop up. There's also this kind of interesting sunlight through a window example with, say, double pane windows and trying to keep sunlight out of houses. That's an energy saving thing these days. And then also this interesting block stacking problem. So the sunlight problem will deal with geometric series as well. And I don't have stems for these because I'm just going to kind of explain it as I go along. And this block stacking problem is kind of an interesting little physics problem. If we want to make a stack of blocks, how far can we make the stack reach before the thing naturally kind of tips over? Or is there a maximum distance that we can make it reach? It's going to actually end up being related to the harmonic series. And I suppose I'll spoil it, but the answer is, in theory, there is no maximum distance. We can stack blocks so that they reach as far as we want them to reach. But remember, the harmonic series goes to infinity really, really slowly. We have to stack an extraordinary number of blocks to reach any appreciable length without toppling over. So, it's something like if you want to go 5 or 10 or something block widths over, You have to have stack blocks like as high as the moon or you know something crazy like that. So in theory, there's no maximum, but unless you have access to lots of spaceships, you know, there's surely a practical limit. Okay, and that's where we'll see this bound, upper and lower bound coming into play. All right, so I will push those last few applications to a supplemental video, so keep an eye out for that. Um, Otherwise, that is, I think, all that I had for today. Let me stop the recording.